This video topic is about transform methods on random variables. Initially, when we learn mathematics in engineering, we have a topic that is for that transform a signal in time domain into the frequency domain, and those transformation can be, for example, Fourier transform or the Laplace transform. What we learn in engineering is that these pair of time domain signal and frequency domain signal form a unique pair, which means whenever you know the Fourier transform, given a Fourier transform, you can also always get back uniquely to the time domain function. So this concept is very similar to what we talk about here. As a transform method, what we're gonna learn in this video is moment generating function and characteristic function. So the transform that we talk about here, um, it takes PDF, positive probability density function, and it transform under this transformation. It gives you a moment generating function, one thing, uh, and by another definition, it gives you the characteristic function. So we can think of these two functions as a transform of PDF. And what's what is a nice thing about this transform method? Because now your PDF function and your MGF function form a unique pair, and the same way for your PDF function and characteristic function. So whenever we want to learn about the distribution of a certain random variable, you can either go to derive its PDF, or you can use the transform technique to first characterize its CF or its MGF first. And then from that expression, you know that because a certain characteristic function is going to be uniquely matched with a certain PDF, so that from that information you can explain about that random variable distribution. Um, these two functions, MGF and CF, have similar definition with some minor differences in the properties. So in this video, I'm going to start with moment generating function definition and how to derive these MGF for a few examples of random variables. First, let's talk about the definition. For random variable f, x mgf or moment generating function is defined as phi t as it takes the argument variable t, and the definition is expectation of e to the tx. Whatever that expectation applies to depends on the type of your random variable. If it is continuous, you take this ensemble average as the integral. So it's going to be integral of e to the tx fx. For discrete, of course, you take expectation as the sum. So it's e to the txk times the PMF of xk. So from this expression, it looks like something that you already know. Laplace transform of time domain signal is going to be e to the minus st ft dt, right? So in this in this expression of MGF, so it looks more like a two-sided Laplace transform of power, not of a probability density function. Okay, and when we take a look at these either infinite integral or the infinite sum here, because that's whatever limit of integration here depends on the range of x, depends on the range space of your random variable. And from this expression, t is a scalar value, is a real number, scalar value. So there's going to be a set of t or the range of t that makes this integral valid. That we're going to see it case by case, and that range of t that makes the integral valid is going to define the domain of your MGF. Um, before going to give you an example how to derive MGF, let's talk about its properties. The reason why it's called moment generating function because actually you're from this phi t, if you know the expression of phi t, you can get all the moments of x as many moment as you want, because we have this nice property that the nth moment of x can be given by taking the nth derivative of phi evaluate at t equals 0. The property in the the property in the yellow box here can be proved very quickly by using the Taylor series expression of e to the tx. So the left hand side is phi t, all right? E to the tx, if we expand the Taylor series of e to the x, you're gonna get a polynomial sum, of infinite terms. And because the expectation operator is linear, you can take it you can distribute it inside the summation. So that gives you expectation of 1 is 1. Expectation of tx is going to be only ex because t is deterministic. And as well as the second term, this and this. And from here, you see that this expression is polynomial in t. And of course, let's evaluate for for phi 0. That gives you, when t is 0, all the terms is 0, so you get phi 0 as 1. What about the first moment? If you want your first moment, let's so by this formula is supposed to be take the first derivative of phi t and evaluate at t0. And as you can see, phi prime t, that's going to give you ex, right? Plus 2t, expectation of x squared, plus 3t squared, 3 factorial, and the expectation of x cubed, and blah, blah, blah. But after you evaluate it as 0, when t equals 0, that's going to give you ex. And if you continue the same process, if I just, how can I undo? Yeah. If I undo, okay. If I keep taking the derivative, all right? If now I take the second derivative, this term goes away. So I'm gonna get the linear term in ex squared, right? And what about the the second term? I'm gonna get 2 times 3t divided by 3 factorial, and this is gonna be expectation of x cubed and dot dot dot. The remaining term, as you can notice, that is going to involve second order function t squared, t cubed, and so on. So once you evaluate at t equals 0, all these higher order terms go away, and that's going to give you e of x squared as expected. Okay, from this property, that is why MGF is useful in this way. It can generate all the moments of random variable. Now let's talk about some nice property about MGF. MGF can also allows you to derive MGF of a transform variable. Let's think about the situation where y is an affine transformation of x, y equals ax plus b. If I apply the definition, if I want to kind of derive the relationship between MGF of y and MGF of x, so I'm going to start with MGF of y at t by the definition is expectation of e to the ty. And then I apply the definition of y, which is affine transformation. Okay. And because so I'm just gonna hold on. Sorry for this messy derivation. And because now we can use the property of exponential function. And because when you take expectation, you must always keep in mind that what is a random variable that you're going to take expectation is a variable x, not other parameters, which means that you can, I mean, for e to the b, it's just deterministic parameter that you can take it outside the expectation operator. So from this relationship, what you can see is that you have the expectation of e to the t a x, but that can simply say that you can read off that because phi xt is e to the etx, now you can read off that this is simply phi of x at at, right? Because this is just a new argument t times a. And that's so the result, it gives you this, all right? Whenever y has an amplified transformation in x, the MGF in y depends on the MGF of x this way with the exponential scaling that comes from the translation term. Okay, we're gonna apply this linear transformation trying to derive maybe MGF of Gaussian example. Okay, we're gonna show it shortly. Now what we're gonna show now is that first of all, I'm gonna derive the MGF of standard normal, and I'm going to apply this property. Okay, if you have, the question is, okay, you have standard normal, and then you say that you apply an affine transformation of a standard normal. The question is, what is the distribution of y? Is it still Gaussian or not? If it is, why? All right. So by using the transformation, the transform method, which is the MGF here, what we can see is that first of all, I'm going to derive an MGF of standard normal. We're going to show in this video that the MGF of standard normal is in the yellow box. And to get to this yellow box is very simple because you're going to apply the definition directly. So expectation of e to the tx is, of course, is the expectation. So expectation of something is integral of that thing times the PDF of x. Okay. But in order to evaluate of this integral, what is the tool to evaluate it? First of all, you recognize this as you just combine the exponent, all right? And you recognize that, oh, it's still an exponential of negative quadratic in x. So this is how you can play with the exponent. And then you can use the trick that you can complete the square. I mean, with the negative quadratic things in x, but the linear term in x, you can think of that as I can still complete the square and it's still a negative quadratic function in x. So what I'm going to do is that I'm just going to complete the square and I just make it up so that it equals to the original term. So that's going to be minus t squared, right? And then I split it back. Okay. So once I have that, I know that this term, I mean, is in the variable t, so it doesn't involve the integration. You can take it outside. and you keep this term inside the integral. How to evaluate this integral? Again, you recognize that you are integrating a Gaussian function that only the mean is shifted by t, right? You still integrate it over minus infinity to infinity. So this is just another Gaussian function with the mean is shifted, right? But the variance is still the same. So you're integrating a PDF that, of course, it must be one. Okay. So um so what we prove now is the yellow box. The yellow box. Okay. Using the same trick, you can also show that the MGF of non-standard normal, the normal with mean mu and with the sigma square, is going to be this expression. Okay. Um, I hope it's not hard. Because what you do is that you can just derive the same way, all right? But now just derive it with the Gaussian um with the e you integrate it, all right? This is a PDF of non-standard normal, but now you multiply it with tx, okay, dx. And now you can use the same technique that I explained earlier. You just like recomplete the square, and it's gonna turn out to be this yellow result. Now, Now, what I'm going to show is that suppose you have verified that the MGF of normal mu sigma square is this yellow box, okay? Now, if I apply this result, because now I can have the same question that so there are two ways, right? Now I have let me just change the box the box color. Suppose I have two results. One result is that I have MGF of standard normal. Second result is I have MGF of a non-standard Gaussian in the green box. I have a parallel question that my X is standard normal. I take an F5 transformation. I take an F5 transformation as y equals ax plus. Now I take y equals sigma x plus mu. I take this, and my question is, what is the distribution of y? Okay, let me just move the text a little. My x is standard normal, okay, and I take the F5 transformation this way. So I can apply the results that I have here. Whenever you have F5 transformation, the MGF of y is given by this. So I'm going to take that result. My MGF of y at t is going to be e to the t translation term times e to the the phi x evaluate at at phi x evaluated at at, which is sigma t. Okay. Because my phi x because my x is standard normal and my phi x is given by this expression, so it's e to the t mu times e to the sigma t square half. See, I have obtained two independent results. I have this question on this parallel setting. I don't know yet which distribution of y is going to be, but I end up having MGF of y according to this expression. All right. Now, on a separate analysis, I have derived MGF of non-standard Gaussian, and it seems that the term in the green box and the result that I just derived in the pink box happen to be the same, right? So from this line, you recognize that this is actually the MGF of a Gaussian, a Gaussian. So that's why in this analysis you can conclude that an F5 transformation of Gaussian is a Gaussian because when you take an F5, you end up having the MGF that looks like an MGF of a Gaussian. Okay. Okay, that's one result. In the last one, I point out that from the MGF of the moment generating function, you can uh, derive the mean EX, and you can derive the second moment according to the formula here. Okay. Before we go to the next topic, um, because in the next video, I'm going to explain that the relationship between MGF and what's so-called characteristic function are very similar. So um, the definition would be, it looks like the definition would be just change the variable t, the argument, into some imaginary number. So, but before we going to that part, I would like to derive a few more example. The question is, what if you have x as the binary, not binary, binomial, binomial random variable? What is the MGF of x? So recall that the PMF of x is n choose k, right? The summation, not the summation, the n choose k, p to the k, and let's call it q of n minus k, where q is 1 minus p, all right? And k takes a value from k takes a value from 1 to n. Okay. By the definition, the moment generating function of x is expectation of e to the tx. Okay. So when x is discrete, binomial random variable is discrete, this expectation is just the sum of e to the tx, right? Which gonna be k in this context because my x takes a value of k from 0 to 1 because that is the range space of my random variable of my binomial. And how can we take this sum? This is going to be another question. This is just use apply any mathematical identities, some math results that you know. When you work with binomial random variable, you always think of the trick is to always think of what we call binomial expansion. You have x plus y to the power of n. That is the sum of n choose k, right? X to the k, y to the n minus k from 0 to n. So in this sum, you take a look at the power of k, right? And n minus k. So it seems like you can group p e to the t together to the power of k, and that is q to the n minus k from 0 to n. So it matches the binomial expansion, and that gives you what is x and y. X in this is p e to the t, y is just q. So it is p e to the t plus q, parenthesis to the power of n. And that is the expression of MGF of binomial random variable. Okay, I think one more, let me just skip. I'm going to derive one more thing, okay, the MGF of Poisson random variable. Suppose we have a Poisson random variable, all right, with parameter lambda. Lambda is the rate of event, and my x takes a value of um, 0, 1, dot, 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 and so on. All right, it's a non-negative integers. My PMF is gonna be uh, lambda to the k e to the minus lambda over k factorial. Okay, that's PMF of Poisson. The question is, what is MGF of Poisson? We start the same way. We have expectation of te to the tx. And now Poisson random variable is discrete, so we use the expectation. K from, now we take the range of x, which is 0 to infinity, e to the tx, right? Which is supposed to be k in this case. And lambda to the k, e to the minus lambda over k factorial. Again, it gets back to this infinite sum, and what's mathematical results we can use to apply and find the sum of this infinite series. You see that it takes a form of something to the power of k, right, over k factorial. The result that you should think of is, we have this analysis, right? You have e to the x, and that's a Taylor series of 1 plus x squared over 2 factorial, x cubed, and so on. That is actually sum of x to the k over k factorial. K start from 0 to infinity. This is the tool you should think of when you're dealing with this infinite sum that takes a form of this. So it looks as if you're taking the sum of lambda e to the t to the whole thing to the power of k. And take a look at this factor e to the minus lambda. That doesn't involve the variable k, so you can take it outside. Let me move a little bit. You can take it outside the sum, and then over k factorial. So it's going to be e to the minus lambda, and compared to this form, so it is going to be e to the, that thing, right? That thing in the parentheses play a role of the dummy variable x here. That is the exponential of lambda e to the t. Okay, so that's it. That's the MGF of a Poisson variable as a function of t. Or you can just, maybe you can wrap it up again. So it's gonna look like this. If you further simplify it. All right. Right. Okay, let me just, how long is it, this video? It's half an hour already. So let me just maybe quit. I just quit at this video, but the connection of the results in this video with the next topic is going to be very related. All right, so keep these results in your notes as well.